So, thank you, everybody, for coming to the One World seminar on the mathematics of machine learning this week. Today, we've got Boris Hanin as a speaker. He is an assistant professor in the ORFE at Princeton University, and he's going to speak about neural nets at finite width and large depth. And
okay, thanks. Thanks for the introduction and for the invitation. Hi, everybody. So before I write anything, I feel that I need to say a couple of words because it's a slightly unusual talk I'm going to try to give. So I've been working for about the last maybe 18 months or so with two really excellent young high energy physicists, Dan Roberts and Yaida, both of who started off doing high energy physics and then went on to do machine learning kind of with their physics background. And so you know, I'm going to report on work that's almost done. It should hopefully be posted at the end of the month. And it's actually going to be this like monograph, basically a textbook, like a research textbook for a slightly physicsy introduction to neural networks, and specifically how to do something really cool at finite width, as I'll explain. Okay, so I'm going to try to be careful. A lot of the things I'm going to say are kind of physicsy theorems. They can certainly be proved mathematically, and some of them I secretly know how to prove, but some of them I don't yet. So I feel like I had to make that disclaimer. Okay, so my plan is I want to introduce the notation that I want to use, and then I want to go as fast as possible to telling you what the problem is I'm trying to solve. I'll give you a little motivation for why I care to solve the problem, and then I'll try to give you a summary of the results before kind of diving into the mathematics. All right, so this is a talk about neural networks. So I have to tell you my notation. And for this talk, I'm going to consider basically the simplest kind of neural network, a multi-layer perceptron, okay, at initialization at the start of training. And if you don't know what that is, I'm about to define it. Okay, so it's not a big deal. So I'm going to draw the kinds of pictures people usually draw for neural networks because they are kind of comforting to me. Okay, so for me, a neural network is a function that starts with an input vector x alpha, and x alpha lives in Rn0. So n0 is the input dimension. And so I'm going to have an alternate name for x alpha. It's also going to be called z0 alpha for reasons that will become apparent in just a moment. Okay, so then the vector of pre-activations at the first layer is what I will call z1 alpha. So this belongs to Rn1. So n1 is my first hidden layer. Okay, and this proceeds until the penultimate layer. So I get a z capital L alpha. And this is a vector in Rnl. And then I have some vector of readouts, which is zl plus 1 sub alpha in Rnl plus 1. Okay, so it's a little unusual, but my subscript alpha denotes which input to the network I'm studying. Okay, and because this network is at initialization, the weights and biases are going to be random. Okay, so more precisely, if we fix some value of the layer index little l, and we fix some component that's neuron number I in layer L corresponding to input alpha. Okay, so let me at least write this once. So L is the layer. There are many indices with neural networks somehow. This is the number of the neuron or the component of the vector that you have. And this is the input. That's what these indices mean. Okay, so by definition, it's given recursively as follows. You take the sum over everything in the previous hidden layer. So J goes from 1 up to NL minus 1. You take your vector of weights, WLIJ. You multiply it by the nonlinearity. So my nonlinearity is sigma applied to the vector of pre-activations at the previous layer. So it's the jth neuron still corresponding to input alpha. And then I add a bias, BLI. Okay, so that's the notation I'm going to use for the recursion. And then the fact that I'm at initialization is just saying that the weights and biases are random. Okay, so specifically for me, WLIJ are going to be drawn independently from a Gaussian with mean 0 and variance that is some constant CW divided by NL minus 1. So this is what people usually call the Hanin normalization. This is kind of at least the standard thing people do in practice. And then my bias vector BLI is going to be also Gaussian with mean 0 and some variance CB. Okay, so CW and CB are just some model parameters, and I'm going to tell you the significance of them in just a bit. Okay, so whatever this is just a stochastic process. It's a vector valued stochastic process. That's the output that I get of the network. And it's built up in this recursive way where each time I apply a random affine transformation and then apply my nonlinearity sigma to every component of the vector in each layer. Okay, so now I can tell you what the problem is I'd like to study, and then I'll tell you why I'd like to study it. So my goal is this. I'd like to compute the joint distribution of all of the neurons in the network. So I'm going to vary both the neural index I, the layer L, and the input alpha. I want the full joint distribution of all the things computed and all the points in your network and all the inputs to the network, and so on, together with derivatives. Okay, maybe I'll write that. So including the derivatives of these objects. And the regime I'm interested in is when the hidden layer widths n1 up to n capital L are large but finite. Okay, so they're all proportional to some large parameter little n. And I don't want to take little n to infinity. I just want to assume it's large. So that's what I mean by finite width. So large but finite width. Okay, so that's my goal. I'd like to understand at the start of neural network training, what does the neural network look like? Okay, I encourage people to maybe put questions in the chat or something. I should be able to relatively easy monitor it. Or you can interrupt if you're feeling very brave. I don't mind that at all. I can monitor both. Okay, so I assume the question is relatively clear, and I want to tell you now why I care to study it. Okay, so let me give you 3 pieces of motivation. Somehow, at first, studying random neural networks. So question, how large is n? Well, let me put it this way. Already when n is going to be 100, I'll be able to make predictions. But ultimately, to give away the punchline, I'm going to have everything written as a power series in 1 over n. And so I'll be able to get all order corrections. And so therefore, any reasonably large n should give you some answers. So the question is derivatives with respect to what? I was deliberately vague. I mean with respect to everything, with respect to inputs, model parameters, one neuron with respect to another neuron, all the derivatives that come up when typically analyzing networks. Yeah, I just mean, the full distribution of everything. So in particular, the NTK will come up and all these kind of fun objects. Yeah, thanks for the questions. Okay, so motivation number 1 is just like this. You might ask, how does the prior that we use for neural network training depend on all the choices that we made? Okay, on the architecture, in this simple case, it's just the width and depth of the network. On these initialization parameters, the nonlinearity, the weight variance, the bias variance, what is good / optimal. Okay, so there are kind of practical questions where you say, look, at the start of training, you're implicitly having some prior, for example, over the distribution of the outputs of the network. And you would just like to know, as a function of the architecture, when is that prior sensible? And once you know something about it, maybe you can even align it to the kind of data you have. That could be a kind of practical motivation for doing this. Okay, so motivation number 2 is a kind of amplification of motivation number 1. And it goes like this. So most networks are over-parameterized. Okay, and that just means they have way more trainable parameters than data points you're trying to fit. And at least intuitively, this means, at least in some settings, okay, this is not always true. So I'll write carefully, I'll say networks sometimes, but not always for sure. Will not move too far. Okay, quote unquote, too far. I'm not really telling you the correct metric here from the start of training from init. So many results, especially of NTK type about networks, say the initialization determines a lot about the way training is going to proceed. If we can only understand initialization very well, training, at least in some contexts, will be a small perturbation around the initialization. So that kind of makes it nice to study. And then the third point to say is that, just because I'm studying the initialization doesn't mean I can't study something about training, even in complete generality. At initialization, you can still compute derivatives, right? You can take derivatives of any order with respect to the time variable and evaluate at t equals 0, of some object you care about. So for example, you can study the early evolution of the neural tangent kernel, or the early evolution of the correlations between neurons, or the early evolution of whatever. And, it's not that all of network training is going to be described as a power series around t equals 0, for sure. But nonetheless, you can get some information about what happens during training as well. Okay, so let me pause for just a second. In part, I want to make sure that people can understand my writing. I'm trying to write relatively small because, it's horrible not to be at a board and have a lot of room. So I want to keep the notation up. But if the writing is so small that no one can understand it, then obviously that's a total disaster. So I'll pause and see if people have questions and things. It's borderline. Okay, so maybe I'll try to write slightly bigger. Thank you for the feedback. At least it's borderline. That's not the worst. Other questions? Okay, so do ask questions, but I will slowly keep going if not. Okay, so I hope I've set up the problem, at least mathematically. I hope I've motivated it a little bit. And now what I want to do is, because I'm trying to kind of, present to you this book that we're almost done writing, it's kind of rather long and there's lots of results of various kinds. So rather than trying to go through all of them kind of in detail, first let me give you a summary and then I'll go through a couple of them. Oh, there's another question. What is the t variable? Oh, that's the optimization time. If you wanted to know what happens after 100 steps of training, you might just say, well, I'm going to linearize training around initialization to a high order in my training variable t, in the time variable, and just see what happens. What's the first order correction? What's the second order correction? And then it's more or less an empirical question, how well that representation actually correlates with what happens early in training. Okay, excellent. So let me do the TLDR. Okay, this is my summary of what we did. Okay, I'm going to try to remember to write slightly bigger. Okay, so TLDR point number 1 is the following. So I told you that my network was wide, but not infinitely wide. And the kind of thing we learned, and this is really one of the reasons I was so excited about this project and why we decided to make a book out of it rather than just write a long paper or something like that, is the kind of techniques that we develop are very generic. I'll say that in a minute. They work for lots of architectures, and they really give you, in principle, a way to answer any question you want at initialization. They're kind of a very broad set of techniques. So let me try to say that at least in some specific way. Okay, so we obtain recursions in the layer index L for the full distribution, okay, of all the neuron activations. So we can only do, at the moment, at least in full generality, we can do a single layer, and we can actually do 2 nearby layers. So we can do the NTK as well, but let me just be precise about that. Okay, so I freeze the layer index L, but I study all the neurons in the layer, and I study all the inputs that I'm interested in, maybe my entire training set or my training and test set or whatever I'm interested in. Okay, so we can get recursions in L. So at all orders in 1 over the width. So let me just write down a formula that will explain why this is a cool thing to be able to do. Okay, so this gives the following representation. So what we learn, and this is the first thing, and then we're about to solve the recursions in the next kind of bullet point, is you might consider the density of this random variable. Okay, let me just, for simplicity, fixate on one particular neuron in layer L at one particular input alpha and evaluate it at some scalar z. So I'm going to write the density of this random variable. So what we learn is the following. If you write it in kind of Hamiltonian form, it takes the following form. So it's e to the minus. So the first term is quadratic, And so this is my notation, KL alpha alpha, as I'll say in just a minute, is just the variance in the infinite width limit. Okay, so there's an infinite width piece, and then there's a quartic correction, like a 5-4 theory kind of thing. But this one comes with a 1 over n in front of it and has a certain constant in front, which we call which the physicists at least call the 4-point vertex. This is VL. And then there's a 6th order correction, which comes at order n squared. And this is related to the connected 6-point function or the connected cumulant and so on. Okay, so in other words, what we learn is the following. So i.e., at order, n to the minus k, you only have to consider the first 2k plus 2 cumulants of your process. Cumulants. Okay, so let me try to say something about that to kind of animate it. So this is the term that survives. That's the only one that survives when you send the width to infinity. And that just corresponds to the fact that in the strict infinite width limit, you get a Gaussian process. Okay, so it's not a surprise that the distribution of a single neuron is just like a Gaussian. But what I'm saying is that there are finite width corrections. And the first correction, for example, the 1 over n correction, involves only adding a z to the 4th term to your probability distribution. Okay, so the higher order terms are higher order in n squared. And so this helps you identify to say at finite width, neural networks are not just some wild thing. They're pretty close to a Gaussian in some explicit sense, where I tell you which cumulants are non-zero. Okay, that's the sense in which it's non-Gaussian. Okay, so that's the first piece, is we can quantify which corrections come in at every order in 1 over n. Okay, but we can do much more. Okay, so we write down recursions for these coefficients, for the k and the v and the w. So these are functions of L. We can write down recursions for them with respect to L. But the observation is now the following. Okay, so the second point is, if you look at KL alpha beta, which I'm going to define right here, okay, this is just literally my notation for the infinite width covariance. Okay, this is the covariance between ZL I alpha and ZL I beta. Okay, so this just means I fix 2 inputs, X alpha and X beta, to the network. I send all the previous hidden layer widths to infinity, and I ask, what is the covariance function of the resulting Gaussian process? I just call it KL alpha beta. Okay, so the point is that this has a well-behaved large L limit. So now I'm interested in deep networks only if these constants CB and CW, so these were the variance of the biases and the variance of the weights, are, okay, so we give it a name, we call it tuned to criticality. Tuned to criticality. Okay, and this just means for me, and I'll show you on the next slide exactly what I mean by this, they're chosen in a kind of very specific way that depends on the nonlinearity sigma. So probably all of you know, if you've studied ReLU networks, that you're supposed to very carefully take the weight variance and make it 2 divided by Fanon. That 2 is the CW for ReLU. Oh, I see there's a question. What orders and what does it mean for them to be at 1 over n? I mean, I just mean that the full probability distribution of the network neurons can be written, the distribution, the full thing, can be written as e to the power series in 1 over n. So that's all orders in 1 over n. I think that answers the question, I hope. So I'm saying that the first order correction in the infinite width limit is the connected 4-point function or the 4th cumulant. And then there's the connected 6-point function or the 6th cumulant and so on. Great. Okay, so I know this is kind of a summary. I'm going to give you some details in a minute, but I just want to try to go through these points so that I can be clear about what the picture is. Okay, so now this tuning to criticality is basically necessary in practice if you want to train deep networks, at least if you don't add batch normalization, you don't add skip connections. This is the kind of thing that is related to a bunch of prior literature. And we definitely have a couple of new innovations that we made, but we borrow from previous work, in this analysis of the infinite width limit. But one of the things that we do that's completely new is the following. Okay, so the third thing is that at criticality, okay, in other words, you tell me the sigma you want, your nonlinearity, and then I tell you how to choose CB and CW in an appropriate way so that the Gaussian infinite width limit is well behaved. We can then actually study the finite width pieces. Okay, so at criticality, we can actually solve the recursions for the Gaussian process covariance, the fourth cumulant, the sixth cumulant, and so on, at any collection of nearby inputs. Okay, so we can write down the recursion. So let me finish the parenthetical actually. So i.e., you get the value, for example, of the neuron, and you get the gradients of the neuron with respect to kind of whatever parameters you want and so on. That's what studying statistics for nearby points kind of gives you access to, is all order derivatives. And so what I'm saying is we can write down the recursions for any collection of inputs. They don't have to be nearby. There can be any number of them and so on. But then we can give very general solutions whenever they're nearby. And then for some nonlinearities like ReLU, for example, or for specific cases like hyperbolic tangent, you can actually solve things more general. But for very general nonlinearities, effectively for any nonlinearity, we can actually solve these recursions for the coefficients that go into this probability distribution. So we're trying to answer the question of what does the network look like? And I'm saying I can actually write down what those constants are. Okay, and we learn the following really interesting thing. And this is one of the main points I want to convey. Okay, so let me write again the thing I had before. I fix a layer L, I fix a neural index I, and I fix an input alpha, and I study the full distribution of what this neuron computes at initialization at a single input Z. I'm doing a single input just because otherwise there's too many indices, but we can do many inputs as well. But here's my point. We get the following refinement of what I wrote above. Okay, so the first term, we can control it. I'll write it the same way. The variance of the neuron, this KL alpha alpha, is well behaved at large L, so I'm just going to leave it as it is. But then the other terms exhibit a very interesting structure. So the next term turns out to be proportional to depth over width times Z to the fourth, plus the next term is proportional to depth over width quantity squared times Z to the sixth, and so on. Okay, so what we learn is that although a priori, this term here, for example, was 1 over n suppressed, and you might say, I don't care about it. Actually, it's not really 1 over n suppressed. It's suppressed by the ratio of the depth to the width. Okay, and this kind of shows the following point. Okay, so this illustrates that depth amplifies finite width effects. Okay, so I'll just give you a couple of examples of this, and that'll be the end of this summary, I promise. Okay, so effect number one. Oh, I see there's a question. Yeah, sorry. So Mark is asking if there are constants in front of here. For sure there are. There are some constants C1 here, some constants C2. But the point is now these constants are independent both of the depth and the width. So there's something we can calculate, and they depend on the nonlinearity, but they no longer scale with any parameters in the model. That's right. Okay, so what are some of these finite width effects? Okay, I'll start with the simplest one. Okay, roughly speaking, the distance to the Gaussian process behavior, the typical thing people will say is that as you send n to infinity, you get closer and closer to a Gaussian process. So it should be like 1 over n. And what I'm saying is that the distance to a Gaussian process actually scales like L over n. That's how the next correction behaves. So the depth and the width fight each other, and deeper networks at the same width are farther from being a Gaussian process. That's the kind of thing I'm saying. Okay, but I can be way more precise, of course. So another thing you can do is you can ask, okay, in the infinite width limit, different neurons, if I take Zi alpha squared, so I take the squared value of neuron I in layer L and I take the squared value of neuron J in layer L. So in the infinite width limit, the neurons are independent of each other, okay, if I is not equal to J. And so this goes to 0 like 1 over n. But actually what I'm saying is this goes to 0 like L over n. And so what you should think is that deeper networks have a kind of a bias towards correlating the neurons in deeper layers. They're by default going to be more correlated the deeper they are into the network. And that's not totally crazy because they share more and more prehistory of the previous things that they've computed. Okay, so a specific example of this is we can compute how the mutual information between two neurons scales. So if you compute the mutual information between this random variable and this random variable, this scales like L over n quantity squared, it turns out. Okay, so this is just another way of saying that as the network gets deeper at a fixed width, you get more and more correlation between your neurons. And now in some sense, too much correlation is bad, some correlation might be good, so on and so forth. Okay, but then let me tell you the final point I want to make about this depth amplifying finite width effects. So this is one of my favorites. So we can do this if you know what the neural tangent kernel is. So let's ask how much does the neural tangent kernel change at the start of training relative to its size at the start of training. Okay, and the point is that, again, you know, the change in the neural tangent kernel usually scales like 1 over the network width. It goes to 0. That's the statement that in the infinite width limit, if you fix the depth, the NTK is frozen and you have a linear model, at least with the initialization scheme that I'm studying. But what I'm saying is that this actually scales like depth over width. Okay, so the way I think about this is that depth cures laziness. Okay, so there's this concept of lazy learning, which I'm sure many people here are familiar with. It's the idea that network training is basically a linearization around initialization. And what I'm saying is that even for vanilla, you know, neural networks, that's not strictly speaking true in the infinite width limit. If you send the depth of the network to infinity together with the width, so that this ratio remains some positive constant, then actually the NTK in that limit will start changing and you'll start learning features in your model and all of this. Okay, okay, let me put one more thing, which I already said, but I can't help myself. Okay, so our techniques, just as a kind of point, extend to residual networks and conv, you know, and so on and so forth. So they're very generic. They only rely on a layered structure to the network. That's the point. But we have not extended them to these things. You know, it was hard enough to get the MLP to work. Okay, so great. There are questions. Yeah. So let me say this again. It's a good question. The question is, I've been writing everything here for a single input because I've been a little bit lazy, and the answer is the following. So let me just circle this key thing. So one thing we can do is we can actually solve these equations, these recursions, and get the same conclusions, to answer your question, if you have any collection of nearby inputs. So we can also sometimes tell you what the network does when the inputs are far away, but that's a rather different calculation. And sometimes it's complicated and we're not 100% sure what the answer is. So there's definitely things we don't know how to do within the framework at the moment. But this observation that things scale like depth over width definitely holds not just at a single input, but for many inputs as well. Yeah, so are there more questions? I don't want to go on to the next part until I've sort of given you a chance to ask me some questions.
Can I? Yeah, I've got a question. So the idea here is that in deeper layers you get more correlation, and you might want some correlation. So you could decide to choose the width of the layer to correlate with the depth to make sure that you get the right amount. But then do the result, so what happens to the L over N? Does this assume that all the layers have the same width here at the moment?
No, okay, so strictly speaking, what I'm assuming is that they're all proportional with uniform constants proportional to N. So you know, one can be 10 times bigger, the other one can be 10 times smaller. But what I'm saying is not going to work if one of them is square root of N and the other one is N. Or more precisely, it will work, but you'll have error terms that reflect that, you know.
Okay. So this analysis is for one scaling of width.
That's right. That's right. And your point about building up correlations is kind of the way we think about it. So there are some things which I haven't written here, which say, if depth over width is too big, then what will happen is you'll run into problems like exploding and vanishing gradients. You'll just have too much fluctuations and everything's going to be bad. So L over N big is not a good regime. But the point is that L over N small is not a good regime either, basically because of estimates like this one. If you want to learn features, you need at least some amount of L over N to be able to do that. At least, again, if you use this kind of standard initialization.
Otherwise, you run into propagation of chaos type things.
Yeah. Right. So, okay, at least conjecturally, this suggests that L over N small but finite is like a reasonable regime.
Okay.
So at least that's a point of view that one could study. Yeah. I see there's no question in the chat. Yeah. So I'm about to explain what I mean by well-behaved. I was purposefully vague on that point. But yeah. So if you give me one moment in the next slide, I will do it. Yeah. So there's a question about empirically. So all of this is, of course, at initialization, and then the question is, well, how much is true after training? And the answer is, I'm not sure. Part of the reason it's a little hard to get exactly the right answer is that typically, at least in practice, people don't use MLPs for at least large tasks, except for maybe in reinforcement learning. I think often MLPs are used for policy selection, but it doesn't matter. And so we didn't check off the shelf with complicated networks. And then, one of the things we're going to do, but just haven't literally done yet, is just train a bunch of MLPs on things and ask exactly the question you're asking. After training, do you see this kind of scaling relation or not? So I'm not 100% sure. It's a totally fair question. Okay, so let me go on. Okay, so I want to now tell you a little bit what I mean by tuning to criticality and sort of how that comes up in the analysis. Okay, so I want to state a theorem which is not ours. Okay, this one was proved by many people before, and I won't give the attribution because there are too many people to attribute it to. But the earliest versions I know of go back to like Radford Neal or something like that in the 90s. And the theorem goes like this. It says, fix the network depth and the weight and bias variances and the nonlinearity sigma. So then, as the hidden layer widths n1 up to n capital L go to infinity, the network output ZL alpha, so this is the full vector of outputs, at all alphas together, converges to a Gaussian process. So this Gaussian process has independent coordinates. Actually, I'll write it this way, has centered independent coordinates. This was a vector in some potentially, high dimensional vector space, but some fixed dimension. Sorry, I should write here an L+1. That was my output. That's how I normalize things, right? With independent coordinates, and it has the following covariance structure. So I told you the coordinates are independent. Everything is centered, so things depend only on the covariance function, right? So I'll write it as KL+1 alpha beta. This is the limit as n1 up to nl go to infinity of the covariance of a fixed neuron, L+1, in the output at input alpha, and then that same neuron at the output at input beta. And I'm going to call it KL+1 alpha beta. And the point of the theorem is not just that you get a Gaussian process, but also you get a nice recursive description of K, okay, which satisfies the following recursion. So K at layer L+1 alpha beta looks like this. It's CB plus CW times this thing, which I'll write as brackets sigma alpha. Sorry, I'll write it this way. Sigma of Z alpha, sigma of Z beta with respect to the previous Gaussian process. Okay, where my notation is just that this means that the vector Z alpha, Z beta is just drawn from the Gaussian process at the previous layer. So it's Gaussian with mean 0 and variance K L alpha alpha, KL alpha beta, KL beta beta. Okay, so this relates the covariance structure at layer L plus 1 to the covariance structure at layer L via this kind of interesting equation. Okay, and this brackets just means expectation. So these brackets mean average. I'm just using the physicist notation for integral. Okay, so the point is that there's this nice way of relating the covariance structure of your Gaussian process in the strict infinite width limit at one layer to what happens at the previous layer. And the point is that, now to be well behaved means that we try to solve this recursion and ask that this kind of dynamical system, these are my variables. If you want, have these three kinds of variables, and this is a closed three-dimensional nonlinear dynamical system, are well behaved. Okay, and there's a standard way to study the stability of such systems. Okay, so you seek stable solutions to this recursion. And the way that one is taught to do this in a kind of first course in dynamical systems basically has two steps. So step number one is you seek a fixed point. So you seek a fixed point for the simplest recursion that you have, which is just the single input recursion. Okay, for K, L, alpha, alpha. And all this means is, I'll call this equation star. I seek a K star so that K star is CB plus CW times sigma squared with respect to K star. Okay, so this is what this recursion comes down to if alpha is equal to beta. Okay, so if you find such a fixed point, what this means is the following. This means that if at the input, the normalized size of your vector was K star, then the covariance, or just the variance in this case, of a neuron in layer L will be equal to K star for all L. Okay, so this is just saying I have a sequence of Gaussian processes. I would at least like it so that for inputs of a certain norm, the size or the variance of my Gaussian process at that input is independent of L. That's one point of being kind of well-behaved at large L. Okay, and then once you found a fixed point, you do perturbation theory around the fixed point, and you ask it to be a stable fixed point. Okay, so let me draw it this way, right? Here I am in Rn0. This is my space of inputs. Here's an input X alpha that belongs to this sphere. Okay, the size of the sphere, I guess, is basically the square root of K star. I'm ignoring my normalization by 1 over N0. And what I'm saying is that if I have a fixed point, then for any input on this circle in input space, the variance of the stochastic process I get at each neuron evaluated at such an input is constant. It's the same variance at every layer. So that's great. But now I ask, okay, now let's perturb in the direction of, the radius of the circle. So I'll call this a parallel perturbation. Okay, so then you ask for stability in the KL alpha alpha direction. Okay, so this says I start with my input X alpha, and I would like it so that for inputs that have slightly different starting norm, the norm also doesn't change to leading order. That's what stability should mean. So just mathematically, this means that the derivative of the variance at layer L with respect to changing the input size evaluated at the input size is equal to K star should be 1 for all L. Okay, and you can easily differentiate the recursion I have above and just get a kind of expression that looks like this. It turns out that this is CW, you take sigma squared double prime K star has to equal 1. Okay, so if you can get this, then you will have guaranteed stability in kind of for parallel perturbation. So I'll call this equation parallel. And the third thing is you ask for stability in the other direction you can perturb. So this is stability in the KL alpha beta direction. Okay, so what this means is I start with my input X alpha, and now I look at nearby inputs of the same norm. And now I would like the covariance between nearby inputs to also remain stable. I want it to be the same as it is at initialization. At the starting layer. Okay, so this is stability in this direction, and it's the same. It's the derivative, but now of the covariance KL alpha beta with respect to changing the initial angle between the points. And then you evaluate this at both points start on your circle of critical values. And in fact, they're very close to each other. So you want this to equal 1 for all L, and you get a similar equation. Okay, I'll call this perp. And you get CW times sigma prime squared. K star has to equal 1. So what I'm saying is that when you start asking what's the best you can hope for from your Gaussian process kernel, you will come down to these three equations. I want the variance to be preserved as much as I can. I want the variance not to jump around too much outside of where it's preserved. That's the stability condition. And then I want the covariance between nearby inputs to be approximately preserved. It turns out that that's the best you can do because you only really have 2 degrees of freedom. You just have CB and CW. Okay, so let me do an example, and then I promise I'll pause for questions. So let's do sigma equals ReLU just to kind of bring this down to earth. So what do the equations look like? So this first equation is very easy to solve for ReLU. Right, you just get, so ReLU of x, just to remind you, is x times the indicator function that x is positive. And so the square of ReLU is just x squared times the indicator function that x is positive. But then this is just a Gaussian integral, over half the line. And that's easy, so you get k star is equal to CB plus CW times k star over 2, right? You lose half the variance because of this indicator function that x is positive. So this is equation star. And then the other 2 equations turn out to give the same condition. So for example, you can look at this second equation. So sigma prime is just the indicator function of the positive half line. And so when you square it, you just get the indicator function of the positive half line. So this equation here corresponds to 1 is equal to CW times the integral of a Gaussian over the right half of the line. So just times a half. Okay, so what do you learn altogether? You learn that there's only one possible solution. CW is equal to 2, CB is equal to 0. And in this case, K star can be anything you wanted. All K stars are preserved. This is what the physicists call exactly marginal. Exactly marginal. Okay, if there's any physicists in the crowd. But it doesn't matter, it's just some words. Okay, so what I'm saying is that this is a kind of very general scheme for initializing a neural network that we can explain exactly how to do numerically for any nonlinearity. It's very simple to just solve or satisfy these kind of conditions. And this scheme tells you essentially the only way to initialize if your goal is to make it so that at each layer, your Gaussian process prior kind of looks as similar as it possibly can to the previous layer. I.e., it doesn't blow up exponentially with the depth of the network. It doesn't decay exponentially with the depth of the network. This is what physicists call criticality. We sort of borrow that from 2-dimensional StatMech. And if there are decays or explosions, they're all polynomial. It's as good as you can possibly get. Okay, so let me pause for a second because this is partly new stuff, partly stuff from the Google Brain Group, as I mentioned. And I think it's kind of cool. So I'm happy to take a question or two on it. And then I'll try to state more precisely 1 or 2 of the theorems that we actually prove. And it'll be sort of an elaboration of the TLDR that I had before. Okay, so there's a question about whether there's a relationship between stability 3 and stability of, I think the question is basically you give me a manifold of inputs, you propagate it through the network and you ask how big is the manifold at the output relative to the input size. So the answer is yes. So it turns out that this quantity here controls the exponential decay or growth of the gradients in the network. Here, I just mean gradients of the output with respect to the input. So if this quantity is not equal to 1, if it's slightly bigger than 1, then all your gradients in the network, and in fact, all of your activations will just be like huge. Okay, I should talk about the gradients. It controls directly the gradients. So the gradients in the network will be massive. They'll grow exponentially with the depth. And that's going to be a disaster for numerical stability reasons. So I hope that answers the question. Other questions?
So I guess my question about the moral of the story for ReLU would be, would this suggest an initialization scheme where you set the bias to 0 and just have the positive homogeneity? Like, is that what's happening here, so that you get a positively homogeneous function in the inputs?
So that's right. Strictly speaking, what this suggests is set the biases to 0 at the start of training for ReLU, and set CW equals to 2. And there's a name for that, right? That's called He normalization or He initialization. This was like invented in a famous paper by Kai-Ming He and some collaborators, where they proposed this and they found that all of a sudden they could train deep ReLU networks, whereas before they couldn't. And what I'm saying is we recover that thing. That's a well-known thing. But the same kind of prescription will give answers for any nonlinearity. That's the first thing to say. And the second thing is to say, if you're slightly wrong about the bias, it turns out not to be a total disaster. The bias is less important in this sense than the weights. So if it was small and positive, you're pretty much safe. But at least to have this kind of exact criticality, the stability of the variance on the diagonal, the fixed point on the variance on the diagonal, and then having the stability of all these perturbations, you need CB equal to 0 for ReLU.
Thank you.
Yeah. Okay, so unless there are other questions, I want to go on and say something about how basically, this recursion here, it's sort of a beautiful thing, at least, okay, I think it's a beautiful thing. And the way I want to think about it is, I want to say it's just the tip of the iceberg. It's just the first part of an entire hierarchy of recursions, where each recursion gets you an extra correction in 1 over the width. So this is the part of the recursions that you have to solve at infinite width. And then having solved this recursion, I'm going to try to solve the recursion for the pieces of the network that are at 1 over n corrected. And then having solved that, you can solve the recursion for the pieces that are 1 over n squared connected and so on. Okay, that's the thing I'm trying to go for, and I want to say something about that. Okay, so let me scroll down to a new slide and put it this way. Okay, so at finite widths, finite values of the network width n, maybe I'll write it like this, ZLI alpha, the distribution of what you get at a neuron somewhere, is not Gaussian. It's not Gaussian, okay, unless you're in the first layer, unless L equals 1. And so we have to consider, we must consider the higher cumulants. I'm not sure how to spell cumulants, it turns out. I think maybe like that. Maybe there are 2 M's, it's hard to say. So for example, here's the first cumulant. So the physicists call this sometimes a connected 4-point function. So I'll call it V, and I know ultimately after doing the calculation that it'll scale like 1 over n L minus 1. That turns out to be the right scaling for it. So by definition, this is, you take the expectation of ZIL alpha to the 4th, and you subtract 3 times the expectation of ZLI alpha squared. Okay, so this is literally the thing that's 0 for the Gaussian. And I'm saying this is one way to try to quantify how far are you from a Gaussian. I forget, there's some name for it, but I forget the kind of crazy names. So V is for 4-point vertex, and this is just a definition. Okay, so this for me is just the 4th cumulant. So let me state a physics theorem. Okay, I'll call it P theorem. There's no crazy physics here. There's no replica trick, and there's no infinite dimensional path integrals. But there are some things that we didn't do as precisely as one would have to get it mathematically right, although I have some idea for how to do it now. So the theorem goes like this, that the kth cumulant of, the stochastic process ZL alpha satisfies the following estimates. Okay, so I'm going to call the kth cumulant kappa KL. So it looks like this. Okay, first of all, it's 0 if k is odd. Okay, that's triviality. That's just because I chose all my weights and biases to be symmetric around 0. So that's not an interesting thing. The interesting thing is the scaling of the even cumulants. So when k is even, it scales like n to the minus k over 2 plus 1. This is when k is even. Okay, so the normalization is slightly funny, but this is what you expect from the central limit theorem, right? This says, for example, that the second cumulant, i.e. the covariance, so when k equals 2, scales like n to the 0. Okay, that's good. That means it survives in the infinite width limit. We know it's supposed to, you get a Gaussian process. When k is equal to 4, you get n to the minus 2 plus 1, so you get 1 over n. And that's this fourth cumulant. And all the other cumulants are further suppressed in 1 over n. Okay, so I'll call this CLT-like. So when you do a CLT for a sum of IID random variables, this is what you expect for the scaling of the cumulants. The physicists call this hierarchical clustering. Hierarchical clustering, for reasons that I actually can't explain. Okay, but here's a corollary of this physicsy theorem. Corollary goes like this, that at order 1 over n, only the second and fourth cumulants matter. Cumulants matter. Okay, so this says basically that, and this is kind of the amplification of what I wrote before, that again, I'll write it for a single input for simplicity, but this is true for any number of inputs. I emphasize that if you don't care about things beyond a first order correction, roughly speaking, you'll have the Gaussian piece that you have to deal with. And then you'll have the quartic piece you have to deal with. So, okay, I won't put all the normalizations. Let me just write it as z to the fourth times 1 over n L minus 1 VL. And then the rest of this can just be ignored at this order. So this is very nice, right? This tells you if you actually want to compute an integral against this, all you have to do is Taylor expand the Gaussian, right? It just means that the full expectation of some function of ZLI alpha is just equal to the Gaussian expectation of this function, f of ZLI alpha, times 1 minus, okay, I just have to Taylor expand this piece, right? I get z to the fourth. Oops, let me just call this a z here. So I don't have to keep writing that. So I should get z to the fourth over nl minus 1 times VL plus 1, Gaussian expectation with respect to just this measure. So this is really a perturbation theory in which full expectations with respect to your non-Gaussian measure are written as integrals against your Gaussian, but you have to perturb the observable or the function you're trying to integrate. Okay, there's a 1 over n correction. That's the kind of thing I'm saying. Okay, so this really lets you do various kind of fun calculations. Okay, so let me give you a flavor of the kind of recursion you get and how to solve it, and then I promise that I will stop. So this is the next P theorem. Okay, so you see that to compute the 1 over n corrections, you have to have a way of computing this V thing, which I called up here this was the V equation. Excuse me. So the P theorem goes like this, is that the cumulants satisfy, okay, let me say relatively simple. They're not that horrible, although they can look a little ugly, simple recursions. Okay, so for example, I get the following recursion for V. So if I want to know the 1 over n correction at layer L plus 1, so this would be VL plus 1 alpha, it looks like this. You get CW squared over NL times the variance of your activation function at the previous layer sigma squared. Notice that these are only Gaussian expectations. Plus you get a certain constant, which maybe you'll recognize from before. Okay, you get sigma squared double prime. And then you get, write it more clearly, you get 1 over NL minus 1 VL alpha in here. Okay, so whatever this is a recursion for V at layer L plus 1 in terms only of the model parameters CW, the Gaussian process at the previous layer. So that's this hierarchical nature of the recursions. You have to solve the recursions one layer up to solve the next ones. So these are just Gaussian integrals I have to do with my nonlinearity. And then a certain constant times V at the previous layer, right? And then notice that at criticality, this constant was exactly one of the things that was supposed to be equal to 1. Okay, you get the following kind of formula. You get 1 over N L VL plus 1 alpha. Looks like this. It looks like a constant over NL. So I'm just simplifying all the things in this first term to a constant because they are constant, plus 1 times 1 over NL minus 1 VL alpha. Okay, so that's a recursion that all of us can solve. And so what you find in the end is that it looks like a constant times the sum on L prime, let's say, goes from 1 up to L of 1 over N L prime. That's how the recursion scales. And as promised, this is like a constant times L over N, when all the NLs have some, N that they're proportional to. So like I said, this 1 over N correction actually is a L over N correction once you solve the recursions. Okay, that's like one of the principal things you learn when you actually write the recursions down. So this analysis can be extended to neurons in adjacent layers. So mostly so far, I've been talking about the distribution of neurons in a single layer. But once you do it for adjacent layers, you get recursions, giving recursions for just because people are interested in this kind of thing, and I'm interested for sure. Okay, so you recover the recursions for the expectation of the NTK. Okay, that's a thing that we get. So, but we recover the infinite width answer, which is known, plus a 1 over N correction, which is new. Similarly, we get the expectation of the NTK squared. Okay, or let me actually put it slightly differently so that it's more clear why I'm doing it this way. So maybe I'll say the variance of the NTK. So previously in the infinite width limit, the variance of the NTK goes to 0 at initialization, but we actually get the 1 over N times some stuff recursion. So we can actually solve it. And we find that it grows like L over N. And we can get the things like the expectation of the time change of the NTK at initialization. And this also grows like, the size of the NTK times L over N, it turns out. Okay, so I'm saying the analysis that I presented is for neurons in one layer, but for adjacent layers, it's not too hard. And you can really get a beautiful formula for the joint distribution and use it to quantify things like the NTK, which always involves smashing together things at 2 consecutive layers. So there's no getting around it. Okay, so I think I've been rambling for long enough. Let me stop. And I'm happy to take questions and have a discussion if people have points or comments they'd like to make.